Oh no. Got it. There we go.
Oh, you done it.
I had it.
It seems to have worked.
There we go. That works.
All right. So thank you all for coming on the 1W-MINDS Zoom. So we're doing a little experiment this time. So our speaker today is Michael Murray, and he's actually at UCSD visiting us to give a talk as the projector freaks out. Great start. So he's going to be giving a talk. We have people at UCSD in attendance, as well as broadcast over the 1W-MINDS Zoom. So Michael will be talking about benign overfitting in neural networks. And we're happy to have him. So Michael, please.
Thanks so much for having me here. Great privilege to talk at the 1W-MINDS seminar and also at UCSD. Like the subject of my talk is going to be on benign overfitting in ReLU networks trained with hinge loss. And this is based on a recent paper that we submitted to NeurIPS. I'm just going to talk about that, I guess, really. First things first, though, it would be very remiss if I didn't highlight my amazing collaborators on this piece of work. So in particular, Erin on the left, then Will in the middle didn't actually send me a mugshot, so I've had to go with the best I can. And then, of course, Diana, who's a professor at UCLA on the right-hand side. None of this work would have been possible without them at all. So really, I'm just here to speak on behalf of all of us. All right, so what am I going to talk about? I'll give a bit of a background on benign, tempered, and catastrophic overfitting. I know this is a subject that some people at UCSD have studied. And in fact, I think this set of terminology originally came from some people working at UCSD. I'll then describe our particular problem setup, go through some of the key results. The projector seems to be, it's resurrected itself. Go through some key results and then give a bit of a deep dive and a proof sketch to really, I guess, highlight some of the main ideas. I'll try and get the talk to about 45 minutes. If you've got any questions at any time, jump in. So benign, tempered, and catastrophic overfitting. I'm going to start with a very simple example to illustrate this point. So I guess the traditional perspective on overfitting looks something a little bit like follows. So imagine I'm trying to learn the identity in this case. So this blue line, and then I draw some samples. And unfortunately, those samples have some noise. I'm not really saying where the noise comes from as yet, but you could imagine maybe there's some sampling error. So we're adding some Gaussian noise as we draw these samples. Potentially also, there's just some features that are hidden from me, so I don't have access to all the information. And so there's a degree of uncertainty in how I make predictions. And then if I try and fit a polynomial model to this set of points, and I try and do some form of interpolation, if I use d equals 5, projector has died again, no worries. If I use a degree 5 polynomial, then the job it does is quite good. And if, okay, projector is still doing stuff, here we go, it seems to be surviving. But you see, it's doing an all right job, maybe not perfectly interpolating the points, but it's pretty close to my target function. So the influence of the noise is not being felt too badly. But then if I boost it up to degree 20 polynomial, it does a wonderful job interpolating the points, but catastrophically fails outside of that training sample, okay? So this is what maybe we would have thought about if someone talked about overfitting. And this is probably the classic example you'll see in a machine learning course, right? So you see this kind of the high degree polynomial flip out and completely fail to generalize, okay? And so really the takeaway, at least from, I guess, my machine learning course I took when I was an undergrad would have been, without some form of explicit regularization, expressive models will fit noise at the expense of the training set, right? Okay, so that's really what I'm saying there in that high level takeaway. But that's maybe not the full story. So in particular now, let's think about a binary classification problem. My goal is just to learn some target function from, say, a vector in RD to the labels -1 and +1. So let's consider d equals 2 in the left-hand side. I've got blue points, which are labeled -1, red points, which are labeled +1. And these are nice and linearly separable. So if I had a vector 0, 1 here, that would do a great job at giving them the correct labels. And so we can think about some training sample, which I've visualized. We're trying to choose some parameters for a parameterized model. I'm going to focus on a single layer ReLU network. Surprise, surprise, maybe if you're doing theory on deep learning. And then, we're going to, I suppose I've talked about this already. Okay, so if we just have the clean problem, so this nice linearly separable binary classification setup, then as we apply a single layer network to this, trained with Adam for 1,000 iterations, we see it does a pretty good job, which is not entirely surprising. And it completely, perfectly pretty much maps minimizes the empirical risk and is going to generalize very well. So now let's make it a bit more interesting, like our regression example, and add some noise. And the way I'm going to add some noise is by resampling and then just flipping some of the points. So this beta I function is going to be a label flipper. And we can see that now we've got some red labels on the left-hand side and some blue labels on the right-hand side. Okay, so now it's mostly true that this problem is linearly separable, but we've got a few corruptions. And we're interested to know how bad is our generalization going to be on our learning classifier by introducing these corruptions. Okay. So with a depth 10, width 10, it's still doing a pretty good job. We're pretty much learning something that's at least approximately the function we want. As depth 100, it gets worse. And then depth 1,000, when we're getting a very expressive network relatively, right? So as our width goes up, the expressiveness of our model is going to increase. We see it really kind of markedly moving away from the target function. At the same time, this is not great, but maybe it's not quite as catastrophic as that first example. And that's maybe the first hint at perhaps the idea that there is a nuance, there is a nuance to overfitting, and it's not necessarily always horrendously terrible or very good. There's some kind of middle ground. And the projector lets me carry on. So the main takeaway I'd say here is that without explicit regularization, expressive models can overfit, but it isn't necessarily catastrophic. Okay. And then finally, the next example I'm going to use is this work from, I think, 2017, which is quite famous now, which I think was something like "We need to rethink generalization." I've got a citation at the bottom. And really, what does this left-hand plot show? It says that the networks or common networks that we use in practice are perfectly capable of absolutely perfectly fitting incredibly noisy data and signals. Okay, so the blue curve, I believe from this paper is KIFR10, so just the uncorrupted KIFR10 data. Green, which is the next best performing, is we apply a fixed but random permutation to every single input image. So we're kind of scrambling our images. Then we've got black, which is Gaussian, which is where I replace my images just with Gaussian images, essentially. So I'm throwing away really any structure. Purple is random pixels. I think this is where they applied a new random permutation to every single image. And then red is random labels, which is, I guess, makes sense. It's the most challenging, where we just resample a random label for each of our images. Okay. So long story short, networks can perfectly interpolate incredibly noisy, unstructured data. And the next kind of experiment they demonstrated was that this doesn't necessarily mean, okay, if it's 100% noise, then of course you're not going to get any generalization because your training sample doesn't contain any information on the test points. But when it comes to test time, if we have just a little bit of noise, things kind of are bad, but not terribly bad, right? So we're talking KIFR10, I think this is AlexNet and Inception. So with 20% label corruptions, so I take 20% of my labels and resample those as random labels, I'm getting something like 30% error. Okay, so not amazing, but certainly not catastrophic, right? There is some robustness to the system. It can still generalize to some extent. And so this has given rise to this space, I guess, or set of, okay, another point, this is not unique to neural networks, as a bunch of works have shown recently. And so this has given rise to this kind of more nuanced view of what overfitting is really about. So we have benign, tempered, and catastrophic overfitting. And these categories of overfitting resulting from perfect interpolation of the noisy data, if we go into them in turn, then when we think of catastrophic, we think just a small amount of noise is going to completely ruin our ability to generalize. And this is what we saw in the very first example. We think tempered as excess risk grows to some degree with the amount of noise we're introducing into the problem. And then finally, the benign case is below a certain noise threshold, maybe. We don't see any cost to our generalization. So in some sense, we're able to learn and generalize perfectly, even though there are these corruptions. Okay. And so our theoretical understanding of this is pretty limited. Okay. Beforehand, we maybe had the bias variance trade-off. We had these very simple axioms and principles, but actually the kind of things we observe in practice, we don't have good theory for, and we really don't know what the impact of the architecture, parameterization, algorithm, the implicit versus explicit forms of regularization that are going on, and the structure of the data, how all of these feed in to actually influence things, okay? So there's a very fast growing body of literature on the topic. I don't want to pretend that we're the only people doing this at all. So particularly in linear models, the purpose of this slide is just to say a lot of people have looked at linear regression, logistic regression, kernel regression, and NTK, and characterize when and how you might get benign overfitting in these settings. What's less studied is the work on neural networks and nonlinear models, which were, I guess, really the initial inspiration for the study. So there's been a few works in this space, but really only in the last 18 months. So starting in about 2022 with this paper by Fry et al. And our paper is the one George et al. That came out in 2023. And you can see in 2023, there were an awful lot of works that came out on this subject. And other works study mostly the logistic loss, which recent results characterizing the implicit bias for logistic loss and in general exponentially tailed losses can be leveraged. This is a work by Telgarsky and some of his PhD students, I think back in 2019. But such characterizations don't exist for things like the hinge loss. And really the reason why neural networks are maybe harder than the linear case is for the linear model, we know in some sense what GD or what SG do, right? We know what the implicit bias is in a linear regression setting. And so we can look at, for example, typically it comes down to some analysis of the spectrum of the pseudo inverse. We don't have that luxury in this case. When we're looking at neural networks, we do have this characterization for exponentially tailed losses. So these have quite a nice, interesting structure. You get convergence maybe in direction, but you never get true convergence. And we know that the direction of the parameters in some sense converges, in direction to the KKT points of this max margin problem. So there's some characterization. It's not nearly as well understood maybe as in the linear case, but there's been some very impressive works that do that. For the hinge loss, though, we have really no clue what it does. And so an interesting question you might ask is, okay, well, how specific are all these results to the particular setting they're in, okay? And so, yeah, we're studying, I guess, this is all of these works are in some sense similar, in a similar spirit, but I'd say this is the key part that sets our work apart, really. Okay, and just to remind someone, so in case you've forgotten what the hinge and the exponential loss look like, the exponential loss is this, or logistic loss is this black line, and the hinge loss is this red line. So if you're familiar with ReLU, think about flipping ReLU around and shifting it along the axis a little bit, okay? And what's important is that the hinge loss does actually achieve its minimizers, okay? So what's our problem setup? Well, we've got a signal and noise decomposition. So we're going to assume our inputs xi. Remember, we're trying to predict labels y in -1, 1. And we're just going to assume an incredibly simple structure, okay? So we're going to have a signal component, which is essentially a signed version of v, some arbitrary vector in Rd, which is unit length. And the inner product of an input with this v gives you, the sign of that gives you the clean label. This is the main idea we have. We then add some noise, so high dimensional noise, which we draw from some isotropic distribution, in particular uniform, just because we want to make sure we can control the comparative sizes. It really just makes the problem nicer. It's not particularly necessary. But the main thing we really want is to have high dimensional noise, which is approximately orthogonal. And the key intuition to how we're going to benignly overfit is that we're going to fit our clean data by looking at this signal component and learning a strong signal, a strong amount of information about the signal in our network, but we're going to fit the few corrupt points by looking in some sense at their signatures, which are these noise points. And these signatures we can think of unique if they are approximately orthogonal. This is the kind of very high level of intuition. Okay, so in our setup, we have this parameter gamma, and gamma controls the, I guess in some sense, the clean margin. So the model I've described, we have this black arrow maybe is along the direction of v, and then we have these orthogonal subspaces to v, which are where the noise lies, and this noise lies on a unit sphere in some very high dimension. So we can think of these kind of two disks, which are separated by 2 square root gamma. And in the clean case, you'd have only blue crosses on the left-hand side, so only positive points maybe on the left-hand side, and only red circles on the right-hand side. But because we've introduced some corruptions, we're flipping some points over. And so this is the kind of the structure of the data we have. So this gamma controls the distance between these two disks. Okay. And with regard to our data, I'm writing up the formulas here. It's not too important, but we're implicitly assuming we've got some 2n points. We're going to make half of them be positive and half of them be negative. So that's why I'm just using -1 to the I. That denotes the kind of clean signal or underlying, clean label. And then we've got this beta I, which is our corrupting term, which only applies to some of our points, right? So we're going to have k corrupt points, and k is much smaller than n. And then our inputs have the following form. And because v and ni are unit vectors, we can see that gamma is, in some sense, trading off the relative size and energy of the signal versus the noise. So when you see gamma, think of signal to noise ratio, really. Okay. All right, so what's our problem set up in terms of the model and training? Well, we're going to be looking at a ReLU network single layer, unfortunately. I would love to be able to talk about depth, but I can't right now. We're going to have 2M ReLU neurons for a similar reason, 2M just so we can make it balanced. M fixed +1 output weight neurons and M fixed negative weight output neurons. And then we're only going to train the input weights, okay? And then we have a linear output layer. So pretty much your most vanilla, boring network you can think of. And then in terms of training, also very vanilla, but we're using the hinge loss this time. So the hinge loss is defined as this. We saw the picture earlier. And then what's nice about hinge loss and interesting is the gradient descent updates actually have this very nice structure. So we can think of every update as being a weighted sum of a particular subset of the points in the training sample, weighted by their sign, okay? So we've got this yi term, and this 1 is meant to be the indicator function. Sorry, that's probably not coming out too well. But we're only going to include a point in this weight update if it satisfies two things. First of all, it's activating the neuron question. So at the previous iterate or current iterate, if you're at iterate t, we're only going to include it into the contribution to the update to the weight at time t+1 if the inner product is positive, essentially. That's what we're saying. And f is if the network is if this point has not been fitted yet. So a point is in f if its loss is less than 1. Okay. So this is quite a nice structure and gives a kind of combinatorial flavor to the problem. And this is why, in many ways, we set up the ni and the vi and the xi so that they're all balanced, right? So xi is a unit vector, and therefore it's just about counting how many corrupt versus positive clean points we have updating a neuron at any given time, right? And the interesting is, as long as in most cases it's more clean points updating the neuron than corrupt, then we can kind of control how this neuron behaves through training, and it acts very much like it would do in the cleanly linearly separable case, which we kind of understand quite well. All right. So the key results, our main results in this work are phase transitions on gamma, so the separation of those two disks. So we're thinking about moving the disks close together or further apart, and what happens to the behavior at the end of training for some fixed noise rate. Okay. And our first result is we can characterize when we have no overfitting. So we're saying when gamma is sufficiently large relative to n and d, so in particular when gamma is roughly bigger than 1/n, so we're thinking if this is quite a large separation, then we're going to see no overfitting, okay? And what that means is that the clean training points are going to achieve 0 loss. The corrupt training points are going to have loss 1, so they're essentially just going to be zeroed by the network. And the network's also going to have asymptotically optimal generalization error. So in some sense, it's basically just ignoring the corruptions in the training sample. Yeah. When we have gamma large, but not too large, so we'll see later what this condition really means is still gamma roughly, or like you can think of for now as gamma like 1/n. Then clean training points are going to have 0 loss. Corrupt training points are also going to have 0 loss. And the network is going to achieve asymptotically optimal generalization error again. Okay, so this is our benign overfitting scenario or case. Finally, then, the third case we identify is this noise dominant regime. And this is when gamma is very small, and so your two spheres are very close to one another, or your two disks. And this means, in this case, the clean training points and corrupt training points both have 0 loss, but sadly, your generalization error has error bounded from below, okay, asymptotically. In some sense, you're never going to generalize well, regardless. Okay, so these are our three main outcomes depending on gamma. And the main one, I don't think we probably have time to go into each of these, and I don't want to go into it in too much detail, but we're going to kind of look at the proof sketch for maybe the most interesting case, which is how we can we can get the benign overfitting result in this setting.
Like, can you say what asymptotic means?
So asymptotically is going to be in the dimension D. So in a lot of these cases, it's going to be, as we make D really large, the problem in some sense get easier. So especially if we're drawing from some isotropic distribution, then the noise terms are going to be, with high probability, more and more likely to be orthogonal. This is a big weakness of this result and many other results, that we're going to need D to be really large. So D is like n squared log n. And pretty much every result I've seen in this space needs this assumption. And that comes from the fact that if we've got n points, we've got roughly n squared pairs, and we need to make sure each of them, and we have to use a kind of union bound. So it's a kind of unfortunate like aspect and really important thing that I think needs to be solved in this space, if possible. A great question. Yeah.
Great. Sorry, I have a really dumb question. I just totally forgot. Is D the dimension of the input data?
D is the dimension of the input data, yeah. Sorry, yeah. M is the number of neurons, N is the number of points, 2n is the number of points, and then we have D is the input dimension. Yeah.
For the harmful overfitting, the corrupt training points out 0, 1, 2.
Yes, everything.
Like-
Oh yeah, that is. Thank you for pointing that out. Sorry, II on the third bullet point should be 0. Thank you very much. Yes. So in the harmful overfitting case, we perfectly interpolate the training sample, but our network generalization error is bounded from below for any D. So yeah, good spot. That's probably a copy and paste there. Apologies. Okay, so before I kind of tell you about some of the maths, then maybe you actually might be interested to see, does this actually bear fruit in practice? Is this at all realistic in terms of what's going on? And I'm going to argue that these 3 plots maybe suggest yes. So the left-hand one gives us the corrupt loss, and we're essentially plotting n versus log gamma. And we can see that in particular for small n, we're fixing D, remember? So this means our training sample is likely to satisfy these orthogonality conditions that we need. And we can see a very sharp phase transition between the overfitting and the non-overfitting case, okay? So we see a very sharp phase transition between these red and black regions. Then in terms of the next, so the middle hand plot, we see a clean loss. And this essentially shows that in nearly all scenarios, we're getting perfect fitting of the clean loss. Apart from the very bottom hand right, where you can see it's a little bit purple, so we're not maybe perfectly fitting all our points, that are clean points as it were. And that's because as n gets large, then our orthogonality conditions start to get compromised. So our results don't quite hold, but looks good so far. And the final one, probably the most interesting, is the test loss on the right-hand side. And there you can see that our theory, if we need, okay, so in general, our theory predicts that log gamma's got to act a bit like minus log n. That's what we said. So it's like gamma's 1 over n roughly. So you can see that this plot, when we fit some curve to it, it kind of resembles this relationship that we're looking for. And once again, see a sharp phase transition between the test loss being high and low, depending on whether our gamma is above or below this line. Yeah. Okay. Slides. So now maybe we have a bit of time for going through kind of how the proof of the benign overfitting result works, what that looks like. And I'll maybe first, before I present that, I'll actually give you the kind of formal results so that I'm not talking so fuzzily about it. And so I'm going to introduce some delta, which is failure probability, and rho, which is going to be the thing that controls the magnitudes of our inner products of our noise. And then I'm going to use lambda w to denote the parameter that controls the norm of the weight initializations. And implicitly in our work, another unfortunate thing maybe you'll point out is that we're going to need lambda w very small at the beginning. And then we're going to introduce some constants c and little c, which are bigger and less than 1 respectively. And we're just saying for some c at the moment, for some constants. We're going to need our number of corruptions k to be proportional, linearly proportional to Cn. But we're going to think of C as pretty small. So k is a small fraction of n. We're going to need d greater than or equal to c rho to the minus 2 log n over delta. So really think of this maybe as n squared log n. And we're going to need to have lambda w smaller than c eta, our step size. Our step size is pretty small, so our initialization, weight initialization is very small. You should think of it like this. Okay. And so what does the actual statement look like? Well, we need n to be essentially just logarithmic with respect to the failure probability. So not very restrictive conditions on n. M needs to be logarithmic in n. So once again, we're not in this very wide regime. We're nowhere near the kind of neural tangent kernel regime. We need our orthogonality condition to be some fraction of the separation between the two clean these two clean disks. And then we need our gamma to be roughly 1/n when you think about it. If you work this through, gamma is kind of, in some sense, proportional to 1/n. That's what this is roughly speaking saying. And then we're saying there exists some sufficiently small step size eta such that with high probability over the randomness of the data sets and also the initialization, we get the following. So we can prove that you do get termination in finite time. So that's a nice thing that we get with hinge loss, and we can bound it from above. We can say that the points, all the points in the training sample at the end of training time have lost 0. So we perfectly interpolate our training set. And then the final thing we'll say is we can characterize the generalization error and bound it from above with respect to C d gamma squared, right? So in particular, if say d was like n cubed, you could think of this as being exponentially decaying in n, right? So the e to the minus n, roughly speaking. Of course, that's bigger than we need, but that's an example to show you kind of as d gets big, and this is going to decay away very fast. Yeah. Okay, so that's a statement. If there's any questions, I can take those now. Otherwise, I can just crack on. Take that as a no, so I will just keep moving. Okay, so what is the kind of main idea? We're going to look at the activation patterns. That's the key thing we're going to use to try and prove the result. And in particular, we're going to say what kind of aiming position might we be aiming for? And the idea is that if my inputs activate neurons of the same output sign as their label in the clean case, or actually in any case, then we're sort of in business, right? So I've tried to draw that here with these diagrams. The kind of deep orange means a very strong activation. So the output from this neuron, when I feed this input in, is large. And so on the left-hand side, I've got positive input, so an input with a positive label. It only activates +1 neurons with strong activation. So when I add all these contributions up, it's going to be a reasonably large positive number. If I take the sign of that, of course, it's a positive label, right? And the same for the right-hand side with the negative labels. Okay, so this is the kind of picture I'm looking for a positive and negative input, and we're going to try and control the activation patterns throughout training and show that we get something that looks a bit like this. Then when it comes to the generalization error, well, because we're in this very high dimensional space, then when we draw a test point, test time, we'll know the test noise is going to be with high probability approximately orthogonal to all of the noise terms that I've seen in my training sample. Okay, and so this means that when I feed that point in, the orthogonal part's going to be pretty much zeroed by the network, whereas the signal component is going to be processed because that does correlate very strongly with the stuff in the training set. Okay, so this is the kind of one of the main tricks of why this very simple data set or data structure kind of works nicely for us. So this is kind of sufficient. If we see a pattern like this with plus and minus v, then we know that we're going to generalize well. That's the kind of idea in a picture. Okay, so at initialization, we of course have completely random activation patterns, but my claim is going to be that one update is sufficient to ensure signal alignment. And I'll describe what signal alignment means in just one second. First, I'll remind you that we're assuming there are n clean, there's 2n minus k, or 2n minus 2k clean points and 2k corrupt ones. And if you're just drawing points samples at average pretty much, and you're drawing neurons, then you can see that pretty much on average, we're going to have approximately n clean points and k corrupt points activating any given neuron, okay? Just through a half space kind of argument. And remembering that n is much bigger than k, yeah? The next thing I'm going to say is that the clean and corrupt points are going to push neurons in terms of their signal direction in different directions, right? So remember, it's yi times xi. This is the update. And the yi, when you take out the kind of sign term, you're going to end up with something that's like -1 to the I plus j plus beta, right? That's one way you can think of it, right? So your corrupt points are going to flip things around. Your clean points are going to push in one way, your corrupt in the other direction. So that's very important. So you've got a large number of neurons pushing one way and a small number of neurons pushing the other way. So the clean points dominate by numbers. And basically all this means is that after one update, the signal component aligns, right? So all I'm saying is that if I take the inner product of wj with v and I multiply it by its sign, it's going to be greater than 0. So negative neurons with negative output weight have learned a minus v component after one update, a small minus v component, but they're nonetheless. And most neurons, positive neurons, have learned a positive v component, right? That's the kind of main idea, right? So what this means is that even after one iteration, I'm getting an activation pattern which looks kind of promising, okay? And so the way we manage this is, remember, lambda w is really, really small. So in some sense, we just want it to be non-zero at initialization. And then we want one update of our gradient step to, in some sense, in some sense, be significantly bigger than the activation at initialization. So we can kind of ignore it. So this is what the positive clean point looks like. You get, just activating a few positive neurons, and the clean negative point is just going to activate a few clean negative neurons. But the loss is still going to be approximately 1, right? Because it's very small activations right now. Meanwhile, for the corrupt points, we see the same thing, but remember it's flipped. Okay, so a corrupt positive point actually has a negative signal component. Yeah. Because it's been flipped. So it's actually going to activate mostly negative neurons, and a corrupt negative point is going to activate mostly positive neurons. The key thing I want to highlight here is that with high probability, if we have M large enough, we're going to have a few neurons which at initialization weren't activated by too many clean points relative to corrupt points. And this is really important because these neurons will essentially carry this point throughout training, right? If I have no positive points activating on my corrupt positive input, then I can't overfit this sample, right? It's not going to be possible for me. So the way we're going to get overfitting is by these carrier neurons carrying these points throughout training, okay? All right, so what do the actual activate, okay, how does the actual dynamics work? I'll first of all highlight this table. And the key thing I want to say is that you can think about the different tensions between the corrupt and clean positive and negative labels, and also the signal and noise component, okay? So the green arrow is the signal component, the gray is the noise. The gray is bigger and the green is smaller because we have gamma roughly 1/n, so actually I should make these quite a lot different. But on the other hand, we have n points pushing in the same direction each time, so they kind of balance it. That's the key tension that we use. But you'll see that in different scenarios, we have them in some sense canceling out, and in other scenarios, we have them acting in the same direction. So in particular, we see that for clean points, the noise and the signal pushes in the same direction, whether it's down or up, whereas for the corrupt points, they're always pushing in opposite directions, okay? So most neurons, as we said, are activated by approximately n clean and at most k corrupt points, and we have k much less than n. The change in the activation from iteration t-1 to t, then, we can look at as follows. So it's going to be plus or minus eta, the step size, and then we have a beta I times n gamma plus 1 minus gamma. So if gamma is really, really small, and it's 1/n, and n is really large, then n gamma is 1, and then 1 minus gamma is approximately 1. So this thing, in fact, is just plus or minus eta beta I plus 1, okay? So because beta I encodes whether the point is corrupt or not, this means that clean points, which beta I is just 1, they're going to change by about 2 eta in either direction, whereas corrupt points are going to change by approximately 0 in each direction, okay? So they're not really moving. Their activation strength is going to remain pretty much the same throughout training, not throughout this early phase of training. Not entirely true. It's a little bit of a white lie, but it's approximately speaking, morally speaking, true. Okay, so what does this mean? So as this early phase of training, and I'm defining phase 1 up until the point I start fitting clean points, what does this mean? Well, it means that my activations for my clean points are over time going to grow. So maybe after 10 iterations, it looks like something like this. Maybe after 100 iterations, it looks something like this. And as the activation strength grows, my hinge loss is going to decrease until finally hit 0, in which case these points are no longer going to contribute. Yeah. On the other hand, my noisy points, as we said, they're not really changing much. Okay, so throughout training, they just look pretty much the same as they did at the beginning of the first phase. Right? And also, because we are learning, we're updating each of these neurons with a lot of clean points, and these clean points all have the signal component pushing in the same direction, the network by the end of phase 1 has learned this very strong signal component. So when I put in plus V or minus V, I'm going to, with high probability, hit or activate a lot of the positive neurons. And for a negative V, I'm going to activate a lot of the negative neurons, okay? So this is looking really good. All we need now is to fit the corrupt points and do so in a way that we don't ruin these nice, pretty activation patterns, okay? So the next part is phase 2. So this begins, of course, after phase 1. And we now think that the clean points are no longer really participating, okay? So they occasionally will switch back on when their loss dips just below 1, but most of the time their loss stays around 1, kind of oscillates around there. We see these kind of bouncing effects. And they don't really, in some sense, their average activation strength is training pretty much 0, okay? Then they're often not actually activating the neuron or participating in the update because they've been fitted. And this means that the corrupt points are now dominated by the, this means the dynamics are dominated by the corrupt points. And in fact, we're seeing most of the time, each neuron is just being activated now by roughly k corrupt points, okay? And so if we just put that into the equation we saw earlier, we now have k gamma instead of, so this is for a corrupt point. We have now k gamma instead of n gamma. And so actually, you can kind of ignore this k gamma as small, it's very negligible. And so it's mostly being fitted by this 1 minus gamma term, which is roughly 1. So roughly speaking, the change in activation of the corrupt points now, the clean points have been fitted, is plus or minus eta. Yeah. And so what does this mean? That means over the next subsequent sets of iterations, the corrupt points, their activations are now going to grow, okay? But they're going to grow on the neurons that they have opposite sign to, and they're going to fall and decay on the neurons they have the same sign as. Okay? So over time, we get something that looks like this. The activations on neurons of the opposite sign are going to slowly decay, while the activation on this carrier neuron is going to get stronger and stronger. So by the end of training, we get something that looks pretty much like this. So after 1,000 neurons, we're now activating just a few neurons of the kind of incorrect label, the corrupt label, and this means we can fit them, okay? And the main idea we have is that the activation of clean points on neurons with the matching output sign, despite that, still remains strong, okay? So we said that their activation wasn't changing too much. And there aren't, and the kind of really technical part of the work in many ways was trying to basically prove that the corrupt points are fitted before they do too much damage to the clean part. Yes, question.
Is this where the dimensionality really becomes relevant?
Not so much, actually. The dimensionality is really about the orthogonality, and that orthogonality means that the correlations between activations are based mostly on signal component rather than noise component. Because if the noise components are perfectly orthogonal, I'm just adding different orthogonal vectors to my weight vectors, and the activation of one neuron only really depends, the activation of a neuron based on 2 points, the correlation in activations is purely driven by the signal component, not by the noise component. That's really the kind of the key part of D.
Okay, but I guess that's what I'm wondering is like if the dimension got smaller, I feel like you wouldn't be able to say necessarily that as you fit the corrupt,
yes,
the clean neurons decay slowly because all of a sudden one of them would get hit really, really hard.
This could, exactly, it could suddenly, if it say this corrupt neuron was really strongly correlated somehow, its noise components were really strongly correlated with clean points of a different sign of other corrupt points somehow, suddenly it could just completely change the, like, in some sense, the distribution of this weight vector over time. So the orthogonality really helps control this, yeah.
Okay.
Yeah.
And a follow-up question on that, have you thought at all about like strange noise models in which you would still get something along those lines, but not involving just a
yeah, this is the main thing. I think for future work, it would be fantastic to move away from this very toy model and study something, you know, a much richer, more expressive.
I almost have to imagine that there would be certain types of corruptions.
Yes.
Where it's not just the points are corrupted, but it's like the points that have particular noise that is orthogonal are corrupted.
And also whether they're near the boundary or away from the boundary, this kind of thing matters massively. And when this doesn't capture any of that, yeah.
I understand how mathematically that would be.
It would be fantastic. And also even just having this linear decision boundary in the first place is something which you want to move away from. And I think there's some actually very recent work that's come out by, I think, Fry and some of the other authors where they do an XOR, and they do essentially a very analogous analysis to this with, I think it's still logistic loss, still high dimension, but they look at an XOR function they're trying to learn. So that's kind of interesting. I think that's the first thing that's moved away from the linearly separable case. But yeah, no, this is the dream. This is definitely what we'd like to work towards. Yeah. Okay, so basically I'm trying to argue that at the end of training, and this is, for us, this was the really, really technical hard bit, which is just trying to prove we don't get the fitting of the corrupt points ruining what we learn in phase 1. And the kind of outshot that we get is that we're actually all right under certain conditions. And we can provably say we fit the corrupt points before they can do too much damage to too many neurons, is essentially the high level summary. And so this means that when we have, as we were saying before, just to summarize, this means when we put in some new noise, this is orthogonal to the noise in the existing training sample. So this thing's pretty much zeroed by the network. And so new points are only fitted on their plus or minus v component. And because this is a nice, pretty picture, this means we get generalization. This is the high level idea. And that's pretty much it. So that is pretty much the end of my talk. I've got a few more slides. I don't know how much time we have. We're about 40.
You're like 40 minutes right now.
40 minutes. Okay, so I have a few more slides we can go through, but maybe we open up to ask questions and then we can, maybe those slides will become relevant. So I have some next steps kind of slide. I have some bits more on hinge loss versus logistic, but I don't know what works.
Awesome. I mean, well, first, thank you for the so questions first. I mean,
so I probably missed this, but was there an explicit dependence of M on N and D?
Logarithmic on N. So the only times we really need M is at the beginning. We need enough neurons that, in some sense, most of them are well behaved. So it's really the condition on M really just arises, I think, pretty much from some kind of pretty basic, just kind of concentration bound argument on the kind of number of neurons which have the right ratio of clean to corrupt points activating them. And that's really the only time, that's the only reason we need M big enough. After that, then nothing else really, we don't really need it. But yeah, it's just that logarithmic on N, which when you compare to say the kind of results you need for neural tangent kernel is like, N to the 4, N to the 6 kind of thing. So we're definitely away from this kind of lazy training, or I'd want to describe in the kind of rich feature learning regime. Yeah.
So first off, a comment. For having to discuss a lot of concentration inequalities, I love the way you actually described the proof because that actually made sense. But I do have a question around like more of the technical aspect of what you were describing is showing that the corrupted points don't destroy the clean label neurons. What is the formalism that goes into that? Because I don't have an intuition of that. All right, I have that intuition, but I don't have an intuition of like what mathematically is occurring.
So at the very high level, it basically says that if my corrupt point updates, or too many corrupt points result in too many corrupt updates, then they're going to switch too many of the clean neurons back on, which will then rectify the issue. It's kind of the intuition. What it looks like in terms of the proof in the first part of our paper, or not the first part, the second appendix, is basically about deriving a kind of a bound based on the current loss on how many possible future iterations can take place until we get convergence.
So it's almost like a control problem where basically if you push them down, they're going to push back up before anything else happens.
But it's a really horrible problem because we have this. Neurons don't die off and turn on gracefully and smoothly. They switch on for an update and they may switch off again. So it's kind of like sorry, not neurons, but points.
Well, so then actually a follow-up to that, is this actually a benefit of using a hinge loss? The fact that basically they turn on somewhat strongly and dominate in the next step so that they turn everything back off.
Honestly, this is one problem, not a problem with the work, but like a weakness. We still don't really characterizing the relative propensities for things like benign overfitting of hinge loss or logistic loss. We can't really answer that question right now. What we're already saying is it does also happen with hinge loss, although the dynamics and the results seem completely different.
So it does happen with hinge loss, and then there were these other papers that showed that the same idea.
The same, like a very different style of proof, but yeah, the same things hold. And in fact, they get it. Yeah, for logistic. Okay. Yeah.
So I have a dumb question. Like, I can't see like how hinge loss is important in the proof because, like, my intuition is that like the ReLU is important because you can characterize the nodes into like activated and not activated. Like, but for hinge loss, I can't see like why this result is specific for hinge loss.
So for hinge loss, the point is that, okay, so you're asking why couldn't we just use what's the difference between the other works? And I'd probably say it probably comes down to these 4 points. So the minimizers of hinge and logistic are quite different. We can actually achieve in finite time, as it were, a global minimizer with a hinge loss. You can't do that with logistic. You're always just converging away to infinity. Because as soon as I find the right direction, I can just keep growing my weights in that direction, and I'm going to reduce my loss. So what does this mean? We also have this position where, in some sense, our result almost relies on you fitting some points perfectly. And then after you fitted those clean points perfectly, you can then fit the corrupt points without too much damage. The original works, they'll typically fit things in some sense at the same time. So original works will consider a ratio of loss. So they'll say, what is the maximum ratio of loss between 2 points? So, loss over xi over xj, maximum over all pairs at ij. And so for us, this is unbounded, okay? We can't derive a bound here because actually we're almost after phase one, we're almost guaranteed to have points with 0 loss. And that's just going to make this ratio completely explode. The final thing is that we don't actually have a correct characterization of the implicit bias for hinge loss. So we do kind of know what the gradient dynamics do in the case of exponentially tailored losses, but we don't really know what this looks like for hinge loss. It's just a different problem. Maybe someone will sometime, but it seems intrinsically more challenging. Yeah, but no, good questions. You can also see just kind of differences, and these are very preliminary experiments, but you can kind of see differences in the dynamics as well. So the absolute values don't really mean a whole lot here, to be honest, because they're just different ways of measuring things. So I'm not really arguing about the way you measure, but you can see that the hinge loss, we get this kind of bouncing, this perturbation. And maybe on the far right-hand side, you could say, well, maybe you need to use a smaller step size, but particularly the first time we start this kind of bouncing, this is due to points switching on and switching off on this boundary of being fitted and not being fitted. So we get quite different looking kind of dynamics in that regard. And you can see that we're seeing quite clear differences as well. We see kind of clear-ish, like a gradual clean loss and corrupt loss following similar-ish curves. Maybe that's unfair because we can't really see with the blue curve involved. But here you can see a sharp kind of wait or delay between the fitting of the corrupt points and the clean points with use of hinge loss. And then, sometimes there's some other pieces where you can look at the correctly classified clean points and you see some differences. I'm not trying to say we have a good answer to the question of does it really make a huge difference? Is one better or worse under some notion than another? But it's in some sense it's not obvious that the two are kind of easily related.
I just want to make sure that the Zoom crowd gets a chance to ask.
I haven't seen any chat online, but
Yeah.
So, hello, One World's folks.
Yeah,
We just want to make sure
there's
ask
no
questions.
question online.
Okay.
List.